Ladies and gentlemen, please welcome NVIDIA co-founder and CEO Jen-Hsun Huang. 请以热烈的掌声欢迎英伟达联合创始人兼 CEO 黄仁勋先生。
Thank you. In 2012, a young researcher named Alex Krizhevsky, working under Geoffrey Hinton in the University of Toronto in the AI laboratory, designed a piece of software that was able to learn visual recognition by itself. It was able to learn visual recognition by learning from a large amount of data using a technology, using an algorithm called deep learning. Deep learning had been in development for some time, some 20 years. But he had a specific insight. He designed this network, and as you know, deep learning has layers and layers of neural net, starting with convolution neural nets, separated by activation layers, where the input is differentiable from the output so that the input could be changed, the weights of the input that affects the output could be changed according to the errors of the output. These neural nets would learn to recognize images or recognize patterns layer by layer by layer by layer by layer. The effectiveness of deep neural net was, if you will, incredibly effective, surprisingly effective. However, the computational requirement necessary to train those deep neural nets was beyond the capabilities of modern computers. It would take months to train a network that would actually recognize images. Alex's observation was that there was a new computing model, a new processor called a GPU, with a new computing model called CUDA that he could apply to this parallel and computationally intensive training operation. In 2012, he designed the AlexNet. And he submitted AlexNet to the global competition of large-scale computer visual recognition competition. And in 2012, when he submitted AlexNet to that competition, he won. AlexNet beat every single computer vision algorithm that was developed by experts, computer vision experts, who hand-coded mathematics, hand-coded algorithms specifically for visual recognition. Without specific training in computer vision, Alex Krizhevsky's AlexNet, trained with data performed on 2 GTX 580s from NVIDIA, and he won the competition. He beat everyone. He beat every single computer vision algorithm that had been developed up to that point, all trained in just a matter of a few days using GTX 580s. The results of AlexNet, his achievements, and the unreasonable level of quality that was able to come out of AlexNet caught the attention of every computer vision scientist, every artificial intelligence scientist around the world. AlexNet, 2012, Alex Krizhevsky, started the GPU deep learning revolution. It was the big bang of modern AI. His work, the results, rang around the world. And I think that moment would have gone down. We will now remember it going down as changing the world. Since then, an avalanche of research has gone into deep learning. In 2012, Stanford professor Andrew Ng and his researchers partnered with NVIDIA Research to develop the first time a very large-scale GPU configuration for deep learning training. Shortly after that, just 3 years later, every single year subsequent to AlexNet, a new network has been introduced, and we continue to beat the world, continue to achieve world records. And now, in 2015, both Google and Microsoft achieved superhuman visual recognition capabilities. A piece of software that was written by software, trained on a GPU, was able to now achieve visual recognition capabilities that are better than most people. Superhuman levels of visual recognition capability for the very first time. And in 2015, Baidu announced that voice recognition had also achieved superhuman levels. Something dramatic has happened. Something very important has happened. For the very first time, computers, writing software by itself, has been able to achieve superhuman levels of the two most important sensory inputs that are the foundations of human intelligence: sight and sound. Sight and sound. To be able to see and to be able to hear, for machines to be able to see and hear as well as humans. We now have the fundamental pillars necessary for us to advance artificial intelligence in a way that has never been conceived of before. If we can't count on the input quality of sight and sound, how can we possibly create machines that can learn and that can behave like humans? For the very, very first time, we believe the foundations are upon us. And this is the reason why it is so important what's happening around us. It is the reason why we believe this is the beginning of the age of AI. Researchers all over the world have seen these results. And there's not one AI laboratory around the world who hasn't jumped on top of GPU deep learning so that they could start to build the foundations of the future of AI. Almost every single researcher has adopted NVIDIA GPUs. And it's all because of this new computing model we call GPU computing. At the foundation of NVIDIA's work is the GPU. We invented the GPU. We're the pioneer of GPU computing. And at its core, what GPUs do is simulate physics, to simulate the virtual world. We use GPUs to create virtual worlds for video games, virtual worlds for design, virtual worlds for storytelling, like film. We simulate the environment, we simulate physics, we simulate how the world should look. We simulate virtual worlds. At the core, you could say that NVIDIA is doing computing of human imagination. Computing of human imagination. One of the most important parts of thinking. And because of deep learning, we are now endeavoring on the other part of artificial intelligence we call human intelligence. The simulation of human intelligence is probably one of the most important works that we have ever done. And we're just incredibly excited about it. And today's conference, our first GTC in China, is all largely dedicated to artificial intelligence, all largely dedicated to deep learning. However, we also can't lose sight of the amazing work that we're doing in visual computing. And so before I get into all of the great announcements and great stories on artificial intelligence, let me first show you the great achievements we have in visual computing. At the core, as a GPU computing company, our most important partners are developers like yourself. And the most important product from our company is the SDK, the Software Developer Kit. It sounds like a very simple thing, but it embodies an enormous amount of work between us and yourself. Rich algorithm work, library work, engine work, breakthroughs and new algorithms are all embodied within the NVIDIA SDK. I'm incredibly excited to show you that the NVIDIA SDK this year includes all kinds of amazing breakthroughs. All kinds of amazing breakthroughs. The SDK now includes the Ansel in-game photography system, so you could actually be inside a video game, inside a virtual environment, and treat it as if it's a real world and you have a real camera, a virtual camera to work with. Volumetric lighting based on physically light models. Optics, which is our ray tracing engine, is now multi-GPU capable. For the very first time, Mental Ray, which is the most popular ray tracer in the world, is now GPU accelerated. Super exciting announcement for the community. Mental Ray is now GPU accelerated. We introduced a new way of capturing materials so that everything you render is beautiful and realistic. By capturing the physical properties of a material, you can now render it exactly as you would see it when you manufacture it. What you render is what you will get. Material description language. We have a sparse volumetrics model for special effects. We have the ability to now render computer graphics on the network and yet composite it on your workstation for broadcast. We have the ability to do ray tracing in VR. The world's first ray tracer for VR. Photorealistic rendering completely in virtual reality. We have the ability to use GPUs to, in real time, stitch a virtual three-dimensional video from 360 video cameras. And also, super excited about our Funhouse application. This is NVIDIA's own first video game, if you will, and we created it with VR. And I look forward to showing that to you in a second. But let me show you a couple of demos now, starting with Ansel in-game photography. Okay? So let me show you, this is a great new game. You're looking at an incredible world. Everything is in real time. And imagine you're playing this video game and you would like to now turn yourself into a photographer, because these video games are now so beautiful, you would like to be a photographer within it. Use it as a form of art. Okay, so let's go into the Ansel mode. With just a click of a button, you're inside the Ansel mode. You could do all kinds of things with it. For example, you could apply filters. All kinds of filters you could apply. Sepia, sketch. This one's fantastic. And of course, we could warm it up, increase the color temperature, make it much more vibrant. We could change the field of view. All of a sudden, you're no longer seeing the world from the view of the player. You can now see the world from the view of a camera, a third-person camera. Now let's pick a place where we like to take the picture from. And suppose let's do a 360. How about let's do a 360 capture? With a click of a button, we could do all kinds of different ways of capturing the movie, including the picture, including VR. But here, let's just do a 360. just like that with a click. And let's go check it out. So we've taken the picture. We get out of the game. We're going to get out of the game, Shitoku. Hello, Shitoku. Okay, so we're now outside of the game. And let's take a look at this photograph. The world's first in-game photography system. You guys know that video games is not just a game, it's a form of art. And it's a form of art that we can share with our friends. And so now for the very first time, you could dump this image out in 360 mode. You could dump it out in VR mode, put it on in your phone. And with a VR headset, you can enjoy being inside this game. It's incredible. Okay, that's fantastic. Thank you. All right, let me show you another demo. This is now in VR. We have, I'm going to be held here by Paul. So Paul is going to get into the VR environment. The first thing about VR is this, and this is a very important capability that NVIDIA platforms provide. Because remember, VR is not just about computer graphics. VR is about being suspended in a virtual world. And you know that virtual worlds have physics. Water behaves like water. Particles behave like particles. When things drop on the floor, it bounces off the floor. It doesn't go through the floor. And when you touch something, it interacts with that object. So the interoperability of the physical nature of the environment and all of the physics simulation associated with that environment has to be done in real time. And so for the very first time, I'm going to show you physics simulation inside VR and its amazing benefits. Let's go ahead and start, Paul. Okay, so first of all, Paul is showing you the goo coming out of this water gun is completely simulated with physics. And so notice when it touches an object, it stays, you could, of course, program the different viscosity and the thickness of the goo, and it interacts with each other. Look at that. Isn't that amazing? Not only is the graphics beautiful, but you also have amazing physics simulations. This is a simulation called a rigid body simulation. And so the bullet coming out of the gun hits one of the porcelain teapots, and the porcelain teapot breaks apart as if it is behaving according to the laws of physics. And so, of course, when you're inside a virtual reality environment, you want that virtual environment to feel like a physically real environment. Rigid body simulations. The smoke that's coming out of his gun is also a simulation of smoke. Twinkie heads. And in this particular demo, the springs are simulated according to the laws of physics. And that's why the springs behave like springs would. The hair, when Paul touches the hair, he could feel it in his hands. So right now where Paul is touching, there's haptics in the controller, and so when he touches these Twinkie heads, he can actually feel that he's touching the Twinkie heads through the gloves. And so the physics simulation makes it much more real. So this is an example of virtual reality requiring a lot more than just beautiful graphics. You need to simulate the physical properties of all of the objects inside the environment and its interactions with each other. Notice the two of them are rubbing up against each other. The two objects, the mathematics, are allowing it to compute collision detection. Okay, that's fantastic. Thank you. Good job, Paul. Now let me show you something else in virtual reality. What you saw just now is virtual reality that suspends you in another environment, and that environment, of course, is not real. There are many types of things that we would like to do in virtual reality that is realistic, but not just realistic in looking, it's actually real. It uses the real data that the original design is from, so that you could actually experience what that design would actually be, what that world would actually be. In this particular example, what I'm about to show you is NVIDIA's brand new headquarters. This is our Silicon Valley headquarters. This is the first of 3 buildings. This building is quite large and will hold approximately 3,000 employees within it. You can kind of see the scale of this building. Now, this building is designed in such a way as to use as much natural lighting as possible. And so notice the entire side of the building is all made of glass, and there's windows up on the roof all over the surface of the roof. We want to find a balance between the light that comes into the building as well as the temperature, of course, because Silicon Valley, as you can tell, as you know, could be quite warm during the summers. And so the balance between light used for natural lighting and light coming into the building to overheat the building, that balance has to be well considered. And to design that building in such a way as to appear attractive, but also to feel very comfortable so that people can work naturally within it. And so the way we solve this problem is we literally took the entire building, the entire NVIDIA headquarters, has been designed and captured inside iRay, inside the world's first physically accurate ray tracing engine. This is the largest object that has ever been inside a virtual reality ray tracing system. This particular ray tracer is simulating so many light rays that it has to run on a supercomputer. And so, as you know, NVIDIA is quite good at building GPU-accelerated supercomputers. iRay is a stack that runs on multiple GPUs, a ray tracer that runs on multiple GPUs. And as a result, we're able to simulate this entire building using the real materials inside the building, real glass, all of the reflectivity characteristics of the materials are all properly simulated. Once we can enjoy this building in virtual reality and physically based simulation, we can really get a sense of what it feels like to be inside. So let me, thank you, Jeff. Okay, so why don't we show them what's inside? So I'm now looking into, let's see here. Okay, so this is inside the building. That's the center of the building. The parking structure is underneath that center. If you look down that hallway, all of the parking structures that are underneath, all of the employees come in through the center of the building every day. Notice the lighting of the environment is quite natural. There are actually no lights that's lighting the inside of this building today at this moment. And you could look at the marble floor, the honed stone floors. You look at the ceiling. And so I think this is going to be set up so that you guys can enjoy it, but you could be inside this building and literally experience what it's like. Every single reflection has been simulated using iRay, the world's largest ray-traced environment, the world's largest ray-traced model. iRay in VR. Okay? There you go. There are a whole bunch of other new APIs in our SDK. I encourage you to go to NVIDIA.com for developers and download the latest SDKs. There are rendering SDKs, rendering APIs and engines. There are physics APIs and engines. There are ray tracing APIs and engines, VR ray tracing, and VR for ray tracing, and VR for games. All kinds of new APIs and SDKs. Really, really important for you to check that out. Allows you to develop applications that takes advantage of the latest capabilities of GPUs as well as the latest breakthroughs in visual computing algorithms. Well, GTC is our most important conference. We're a GPU computing platform company, and developers is the most important thing, SDK is our most important product, and GTC is our most important event. If you take a look at the growth in the last several years, the growth has been utterly staggering. This year, GTCs would have welcomed 16,000 attendees from around the world, not including all the people that enjoyed the content and the tutorials and the labs and all the talks and the keynote from the web. These are attendees who showed up here like yourself. 16,000 this year compared to 37,000 just 2 years ago. The number of people who downloaded our SDKs, the number of GPU developers, increased by a factor of 3 to over 400,000 developers on GPUs now. These are software developers, researchers, designers, game developers who are now using GPUs to develop their software. And this software is enjoyed by hundreds of millions of people around the world. But the most staggering number is actually the number of deep learning developers. 25 times increase in just 2 years. The number of developers that have downloaded cuDNN, our deep neural net and deep learning library and engine, has increased by 25 times and has been downloaded 55,000 times. Well, what are people doing with it? A lot of it is higher ed. AI researchers from all over the world. There's not one AI laboratory that I know of today that doesn't use NVIDIA's GPU platform for their AI research. Software companies could be internet software providers, internet software such as Baidu software for voice recognition would be among those. And then, of course, internet companies, auto companies, governments, medical for imaging, for image recognition, for medical imaging, as well as finance and manufacturing. The number of fields that GPU deep learning is touching is really quite shocking. Well, you got to ask yourself, I guess, at the core, why is it that AI researchers have adopted GPUs? Well, we know exactly why Alex Krizhevsky found it. It's because the parallel computing model of the GPU is very consistent with the needs of his deep learning network. But the question is maybe a little bit deeper than that. Why is it that the GPU was such a perfect fit for deep learning? And there's of course going to be a lot of science and a lot of research in this area in the coming years. But let me give you maybe a tongue-in-cheek, a not-so-serious example of why it is. It's possible, that your brain is in fact a GPU. So for example, when I ask you to think about ping pong, and you close your eyes and you think about ping pong, it is very likely that your brain generated an image of a couple of people playing ping pong. If I asked you to think about Kung Fu Panda, and you close your eyes and you thought about Kung Fu Panda, it's very likely that we all thought of a similar Kung Fu Panda, that our brain generated computer images in our brain. We call them mental images. It is also the case that our GPU is structured kind of like our brain. Instead of one very, very powerful processor that's operating sequentially, our GPU has thousands of processors, smaller processors, that are trying to solve a problem together. These thousands of processors are doing mathematics and connecting with each other, sharing information with each other, ultimately solving one large problem, a little bit like a brain. So the brain is a little bit like a GPU in the sense that it generates images, and our GPU is a little bit like a brain. And so maybe it is the case that this new computing model to solve artificial intelligence is a computing model that is perfect for GPUs. That GPU deep learning is this new computing model, and the GPU is the perfect and the ideal processor for it. Now, deep learning is a new computing model, and it's going to touch all aspects of software. Deep learning starts with, of course, developing and designing the network and training the network. We call that training. However, once the network is trained, and that training of the network requires billions of trillions of operations. You're taking a network that is already very, very large and computationally very complex. You have millions and millions and millions of samples of data that you would like to train this network with. And so that could take a very, very long time. Without a GPU, it could take months. With a GPU, it would take days. That's one of the reasons why the GPU allows you to either create much more sophisticated models that are more accurate, or it allows you to get to market as soon as possible. Training is the foundational part of deep learning. Once you have that network, once you have the network, then of course you want to apply that network to infer, to predict, to classify from a query, okay? To infer from a piece of information. To infer from a piece of information could come from the queries of all of our access of the internet. Billions of people making tens of billions of queries around the world every day, and these could be images, it could be text, it could be voice, and in the future, and increasingly, it could be live video. GPU inference in a data center needs to be very fast so that the experience is responsive, and it needs to be very fast so that the throughput of the data center is as high as possible. Data center inferencing, the second part of deep learning. So the first part is training. The second part is inferencing in a data center. The third part of deep learning is what some people might call IoTs, intelligent devices. These networks that have been trained can now be embedded inside devices. It could be a camera, it could be a car, it could be a robot, it could be a microphone. And it turns that device, that connected device, into an intelligent device. IoT is fundamentally going to be driven by artificial intelligence, and IoT is fundamentally going to be powered by deep neural nets. We're going to see billions and billions of intelligent devices, and the fundamental goal here is to be able to recognize, classify, interact with commands in the environment, do it very quickly, do it very accurately, and do it with as little power as possible. These three segments of computing are all going to be shaped by deep learning in the coming years. Software development is going to be different than it used to be. The way that we run software will be different, and the type of operations that we run in the devices that are around the world will also be different. Deep learning is going to touch every aspect of computing. Now, starting with training, let's take a look at training and its complexities. I already mentioned that training is billions of trillions of operations. The more data you have, the larger the model that you use, the more accurate the results will be. Jeff Dean's presentation, Jeff Dean at Google, he's their chief engineer, said that more data plus bigger models plus more computation will lead to better results of deep learning. And that's pretty fundamental to training. And if you take a look at some of the trends in the last couple of years, Microsoft's recent image recognition network called ResNet was introduced in the year 2015. If you compare that to AlexNet, AlexNet had 8 layers. This deep learning network had 8 layers. Its processing, combined processing inside that network is 1.4 billion operations per second. And it achieved an error rate, meaning that how often it was wrong, 16%. Okay? So 8 layers, 1.4 gigaflops, the total mathematics in the network, and it was able to achieve an error rate of 16%. What that basically says is this. If you have and that was the best in the world. If you have a computer vision algorithm that was written by computer vision experts, most of the error rates are much worse than 16%. And so that tells you about the limits of using computer vision for applications like self-driving cars. Using traditional computer vision approaches, the limits by which you could achieve accuracy is surely limited to something that is unacceptable for all of us from a perspective of safety. However, using deep learning, in the last several years, we've been able to achieve an error rate of just 3.5%. 3.5% tested among millions of images. 152 layers. 8 only a few years ago, 152 layers today, and a total computational capacity of that network of 22 billion floating point operations per second, an increase of 16 times. This states the deep learning problem. In just literally 3 years' time, the computational load of deep learning has grown 16 times. Much, much faster than Moore's Law. The problem is getting harder and harder, and yet computational capability is not growing as fast. That's one of the reasons why the entire industry has looked for a new computing model, and that's why they've all reached out to GPU computing. This is for image recognition, an increase of 16 times in just 3 years. This is staggering here. This is voice recognition. As you understand, voice recognition is the foundation of natural language understanding. And natural language understanding is the foundation of intelligence. If we can teach a computer to understand, not just recognize, to understand the meaning of our words, that computer will be able to learn by itself, by reading books, by going to the library, the world's libraries, and just simply read every single book as fast as you know how fast a computer can work and learn and get smarter all the time. Natural language understanding is one of the most important areas of research in AI, and voice recognition is at the foundation of it. Baidu's work, this is the work that is done by Andrew Ng and his lab, Deep Speech 1 in the year 2014 had 25 million parameters inside that model. It was trained on 7,000 hours of speech, and it achieved an error rate of 8%, which means that every 10 words was a mistake. 1 out of every 10 words, 1 out of every 12 words. In 2015, by training it with nearly twice as much data and creating a network, a deep learning network that is 4 times larger, twice as much data, 4 times as much parameters inside, 4 times as much complexity, it was able to achieve an error rate of 5%. In just 1 year, Baidu's Deep Speech 2 reduced the error rate by 40% in just 1 year. However, the price to pay was the amount of computation, 20 exaflops. 20 million, billion floating point operations was necessary to train this network. As you could see, the amount of computation is precisely the reason why this unreasonably effective approach called deep learning has taken so long to emerge. Until GPU deep learning came along, until the big bang of AI came along, this approach would have been computationally prohibitive. No computers in the world could have trained these networks until the GPU came along. And that's one of the reasons why we're all so excited about this new computing model and why this moment in time in the computer industry is so vitally important. Also recognizing that this trend will likely continue. Remember, we're at 5% error rate, but we would like to get to 0% error rate. Recognizing everybody's voice, recognizing beyond that, recognizing and understanding the semantics, the meanings of the words. We have much, much computation to go. Recognizing that we will continue to advance AI at this amazing rate, we have invested in the last several years in the single greatest endeavor in our company's history. Pascal is the world's first GPU that has been optimized for deep learning, that has been optimized for AI computing. There are several things that we did. The first thing is that the processor of Pascal is truly a miracle. The processor of Pascal is truly a miracle. It has a brand new architecture. It uses three-dimensional transistors called FinFET. It used three-dimensional packaging and used three-dimensional memories stacked on top of each other. All of it in combination made it possible for us to take a giant leap forward in performance with Pascal. Brand new architectures, brand new instructions, brand new manufacturing process for semiconductors, brand new packaging, and as well as a new interconnect that connects multiple GPUs together so that they can work together as a team. Not to mention a whole bunch of new deep learning algorithms. Pascal was such a great achievement and has taken NVIDIA 3 years and 10,000 man-years to achieve Pascal. This is our single greatest endeavor. To go along with Pascal, we realize that the processor is just the beginning. That with AI computing, with this new computing model, even the computer system architecture will change. Processor design will change. Algorithms will change. The way we develop software will change. And we believe system design will also change. We created a brand new computer, a supercomputer inside just one box, an incredible achievement we call the NVIDIA DGX-1. It is an AI supercomputer, and it replaces approximately 250 servers. So basically, an entire data center shrunk into one small box. This particular computer was designed completely from scratch, from the ground up. DGX-1. The combination between Pascal, the processor, and DGX-1 allowed us to achieve an increase in performance in just 1 year of 65 times relative to the first time that Alex Krizhevsky used NVIDIA GPUs to train his deep neural network. 65 times since deep learning was first discovered. This is way faster than Moore's Law, way faster than semiconductor advances, way faster than any advance in the history of computing that we've ever seen. And all of this so that we can sustain and continue to advance deep learning in all kinds of fields. Our processors are all completely architecturally identical. And so whether you have in your PC or laptop, it could be in the cloud, in a hyperscale data center, it could be in a DGX-1 supercomputer, it could even be in a small little embedded computer. They're all architecturally accessible, all architecturally compatible, all based on the NVIDIA GPU computing platform. As a result, every framework that we know, every framework in the world, and there's some, I think people say that there's some 100 frameworks. There are frameworks that are optimized for images. There are frameworks that are optimized for voice and language. There are frameworks that are optimized for ease of use, and there are frameworks that are optimized for large-scale performance. There are all kinds of frameworks. Frameworks are going to start emerging that are application-specific. Some will be for finance, some of it will for energy discovery, some of it for manufacturing, some of it for IoT, some of it for training robots. These frameworks, basically the tools of AI, have all been optimized for NVIDIA. And so whether it's processor performance, system performance, a dedication to continue to advance this field, or the adoption of our architecture by every framework in the world, this is the reason why NVIDIA's architecture is the most adopted architecture for AI computing today. I'm delighted to announce that the world's largest enterprise computing company, IBM, the company that first started to talk about cognitive era, the era of artificial intelligence, the company that we know has been in computing since the beginning of computing, has joined us and adopted NVIDIA's architecture, the NVIDIA Tesla architecture and the NVIDIA NVLink interconnect architecture, in combination with their Power 8 CPU, the most powerful CPU in the world today, to create a computing platform for AI in the enterprise. We're super excited about this partnership. We can now take this basic architecture, not just from hyperscale and consumer app and researchers, but to span it and scale it across enterprises all over the world with the partnership of IBM. Let's welcome them to the NVIDIA platform. And so the first part of deep learning is really about performance. It's really about continuing to be able to train larger and larger networks with more and more data, and yet still be able to achieve many iterations and be able to get that network to market, because ultimately, applying that network is what it's all about. I can't imagine anyone better to talk to you about the importance of deep learning, the implications of computing to this incredible new field, than somebody who's been in it since day one. Andrew Ng is one of the world's renowned researchers. Yeah, please. Yeah, let's give our hands together. They didn't even give me a chance to say all kinds of nice things about you. And so I'm going to say all kinds of nice things about Andrew while he's standing next to me.
Great. Not awkward.
All right, you guys know that Andrew is one of the world's renowned researchers in AI. He is the chief scientist of AI for Baidu. He is the head of Silicon Valley AI Research Center. And he has contributed so much to deep learning. And we started working together 5 years ago as a result of recognizing that deep learning is going to need much, much, much more than what computing applied available at the time. And it was the research that we worked on together that scaled very large-scale GPU clusters that really made it possible for practical deep learning to be applied today all over the world. So his contributions has been enormous. Let's give him another round of applause. He's going to talk to you about deep learning.
Great. Thank you, Jensen. Oh, Jensen? Jensen, I get the Jensen. 哦，这个遥控器，对，好，遥控器。Oh, yeah, 好 ，All right, I'll use Jensen's. Thank you. 大家好。那么其实其实我觉得现在我们再说一句话，就是 AI is the new electricity。意思就是100年前电能改变了很多不同的行业，我觉得现在人工智能也会对很多行业带来一样大的改变。那么现在人工智能非常大部分都是需要依赖 GPU， 就是 Jen-Hsun Huang 和 NVIDIA 的工作。我今天就想为大家分享一下这是为什么的，也为大家分享一下这个人工智能对你们的工作可能会有怎么样的影响。不过其实我觉得我今天还是跟着 Jensen 一样，跟大家讲英语。其实在中国我已经好久没有用英语来演讲，不过我今天试一试讲英语吧。You know, but Susie, I think all of us in the AI community have been very fortunate that very early on, before it became obvious how important deep learning will be, Jensen dedicated a large fraction of NVIDIA to building this amazing GPU platform that has made so much of the progress at Baidu and at many other companies possible. So at Baidu, we think that we've gone from the PC era into the mobile era, and that today we are going from the mobile era into the AI era. And so one of the things I've been very interested in doing is to help really everyone, to help all of you, to help lots of businesses enter this AI era. This is why about 2 weeks ago at Baidu World 狮子大会 with Jen-Hsun with us, we announced that we're taking a lot of our best AI technologies, 包括我们的语音、图像、自然语言处理、用户画像、机器学习的技术，都输出来为大家提供服务。And all of these technologies, almost a very large fraction of these technologies, were trained using machine learning and deep learning, specifically on top of GPUs. So you've heard a lot about deep learning, right? So what is deep learning? And as Jen-Hsun said, those of us that work in deep learning often make an analogy to neurons in the brain, that maybe neural networks are a little bit like the human brain. So I wanted to go a little bit deeper into the technical details to explain what is a neural network and why we found GPUs to be so well suited to training these neural networks. So if I draw a picture like this, right, what does this picture represent? Does it input a face? There are all these neurons, and then we output, is this a face or not, right? 就是人脸识别, face recognition. So what this picture represents is each of those dots is a number. So each of those layers of the neural network represents a vector of numbers, like x1, x2, x3, x4, x5. And between each of the layers is also a matrix, W1, W2, W3, W4. And almost all the work of a neural network, right, almost all that this picture represents is taking those vectors, x, and multiplying them by these matrices W, and maybe taking the positive part of it. Right? And so it turns out that 99% of the work we do in deep learning is multiplying matrices and matrices, or multiplying matrices and vectors. And it turns out that GPUs, because of their ability to carry out high-throughput parallel computations, have from day one been remarkable, incredibly efficient at matrix multiplications. And this is why the whole deep learning community is jumping onto GPU as a platform to do this work. So, there's a lot of hype, right? 我觉得人工智能也有点炒作. There's a lot of hype about AI. So what is AI? What is deep learning really? It turns out that almost all the economic value of AI today is from one type of machine learning called supervised learning, or 监督式学习. So what is supervised learning? Right? 监督式学习的意思就是你学习你输入什么就输出什么 learning X to Y mappings. 比如说人脸识别 right? If you want to train a face recognition system, then we give it a data set like this, where we give it examples of faces. Yes, that's a face, not a face. And we train these neural networks by multiplying a lot of matrices together to fit this data. And this is how we do face recognition. In fact, a lot of the economic value of deep learning today is finding very clever ways, 找到非常聪明的办法来使用这个监督式学习 right? And 右边我又写了比较多例子。比如说，如果你想识别出，如果你有一些用户评论想识别出它是不是垃圾邮件，就可以用监督式学习来训练。如果你有足够的数据，如果就在百度，如果你看到很多有关用户和广告的信息，也可以识别，也可以训练一个模型来预测一个用户会不会点击一个广告。So all of these. Finding clever ways to use supervised learning has driven tremendous economic value in Baidu and in a lot of other companies. And just this formula of supervised learning is enough to transform industry after industry. It turns out that there's a lot of basic research that we're working on, that other teams are working on unsupervised learning, on reinforcement learning, on many other forms of learning. And I hope we'll have breakthroughs in those other areas as well in the next few years. But this formula of 监督式学习 is enough already to transform probably a lot of your work. Everything I've said, right, I could have said almost all the technical details that I presented so far, I could have presented 20 years ago, right? So far in what I've said, there have been very few new ideas. So why is deep learning taking off now? I think that the biggest trend, the number one reason that deep learning is taking off just in the last several years is scale. And so I like to make an analogy to building space rockets. I think building AI is like building a space rocket. So what is a space rocket? To build a rocket, you need a huge engine, right? 巨大的引擎, and a huge amount of rocket fuel. And both need to be huge. If you have a rocket with a huge engine and a tiny amount of fuel, you won't go very far. If you have a tiny little engine and a huge amount of fuel, you might not even lift off. It's only with a huge engine and a huge amount of fuel that you can build a great rocket. So the analogy is that the rocket engine is the huge neural networks that we're now finally able to build, thanks to really Moore's law and scaling much faster than Moore's law with advances in GPUs. And the rocket fuel is the huge amount of data that leading internet companies and many of you probably now have access to. And so algorithmic innovation has been important too, but one of the most reliable formulas for improving machine learning progress is build a big network, give it lots of data, right? So over the past several years, this has been some trends I saw, right? Just as the community, as we drove scale of machine learning. About 10 years ago, most of us were training neural networks on normal CPUs, and back then we were training networks with about 1 million connections, so progress was slow. About, I guess, 2008, we wrote our first paper on training a neural network on CUDA. And so that allowed us, this was at Stanford, to scale up neural networks about 1 order of magnitude, right? And then I think 2011, when I was leading the Google Brain team, we used CPU computing to scale this up even more with many CPUs. But shortly after, we realized that cloud computing, many CPUs, is not a good way to scale up deep learning. And so at Stanford, and then later at Baidu, we realized that using HPC, right, 高性能算法, and more recently, the supercomputers is a much more promising way to scale up these deep learning algorithms. And so I think that the bleeding edge, really, the most advanced deep learning systems today are shifting to HPC, to high-performance computing. To give an example, to train our speech recognition system today, it takes about 10 exaflops, actually maybe 20 exaflops. So there's 10 to the 19 flops. It costs us about $100 of electricity just to train one model. When one of our researchers trains one model, they spend about $100 on electricity. And we train on about 4 terabytes of data, now up to about 50,000 hours of data. And so I think at Baidu was the first company, first large company to build a GPU cluster for deep learning. 我说的意思是全球第一，不只是中国第一, right? We're also the first company to announce, first large company to announce putting GPUs into production, not just training, but serving. And I think our early investments, our early bet on GPUs has enabled us to sustain a lead that has helped our researchers and our AI capabilities. So I want to go into just one case study, go deeper into one example of how deep learning is transforming many AI applications at Baidu. And the example I'm going to talk about is the speech recognition, right, which Jen-Hsun also mentioned. So traditionally, speech recognition systems had many stages. You'd input the audio, extract the audio features, extract phonemes, and then have a language model, and then output the transcript of what a user said, like the quick brown fox jumps over the lazy dog. So in 2011, Li Deng and Jeff Hinton realized that they could take the first stage, the 语音特征, and replace that with a neural network. This was great progress. At Baidu, building the deep speech system, what we said was, let's take these decades of work of speech recognition, and let's forget the whole thing and blow it away and replace it with a neural network. And we found that with a big enough rocket engine, with a big enough neural network of this structure, using this end-to-end 端对端学习方法, this allowed us to train our best speech recognition systems. In this picture, I gave a slightly simplified image of our speech recognition system. The real system actually looks a bit more complicated. There's a bidirectional recurrent neural network with a CTC cost function, but this is our most effective speech recognition system today. So let's see, there was some audio. Okay, good. So what I want to do is give you a demo of our speech recognition system. What I want to do is invite you to listen to a piece of audio and see, right? 想请大家听一段语音，看一看你个人识别可不可以识别出这段语音的人在讲什么。Could you please the audio?
大骆驼的第一季。
他在讲什么？哎，在。
大骆驼的第一季。
那么我们语音识别系统之属。再听，好，让大家再听一次啊。
大骆驼的第一季。
听到了吗？谢谢。再给大家听第二个例子，请播放。
胎动厉害，不去吸氧可以吗？
哎，讲什么？是什么是可以吗？再听一次。
胎动厉害，不去吸氧可以吗？
如果我们把这段语音放进去我们的 Deep Speech 语音识别系统，它就输出这句话。再听一次啊。
胎动厉害，不去吸氧可以吗？
啊，听到了吗？谢谢。所以我们现在的语音识别能力已经超过一个正常人的识别能力。其实刚刚上个月我们跟Stanford University 斯坦福大学和 University of Washington 合作，也发现如果你想用手机来输入某个信息，用语音识别是比用这个键盘可以快3倍。那么这些结果呢，可以做得好，都是依赖我们的 Deep Speech 2系统，也是依赖NVIDIA 的 GPU 来训练的。So, you know, we've talked a bit about the importance of scale of data, scale of computation for training these deep learning systems. In fact, I want to present to you a simple recipe, right, for driving, for improving machine learning systems. And this is a little oversimplified, but when my teams ask me for help with improving their machine learning system, the first thing I do is present to them this recipe. So the first thing I do is ask them, you know, are you doing well on the training set, right? And if not, then I tell them, you know, build a bigger neural network, so get a bigger rocket engine. And you keep doing that until you are doing well, at least on the training set. Once you're doing well on the training set, I ask them, are you doing well on the test set, right? If not, I tell them, try to get more data, you know, get more rocket fuel. And you just keep doing that until you're hopefully doing well on the training set and on the test set. Now, and it turns out that this very simple formula, the world is more complicated, this is oversimplified, but this very simple formula drives a lot of, is enough. It has been enough to help us and is enough, I think, to help you improve the performance of quite a lot of machine learning systems. But a lot of recent progress in machine learning the last several years has been due to scaling up data and scaling up computation. And a lot of the computation was made possible only because of GPU computing. I should say the world is more complicated than this simple picture. So for those of you that want, you know, a more nuanced, a more complex view on how to improve machine learning performance, there's a book I've been writing that you can get a free draft of from that website. So we've talked a lot about using GPUs for training. And I've seen this have a huge influence on Baidu's work and on the work of a lot of other companies. One of the trends we're seeing is starting to use GPUs not just for training, but for online service, 来提供在线服务。So, 其实，在百度，我们使用这个 HPC 训练了巨大的神经网络以后，我们就发现我们有一个问题，就是我们怎么样可以把这么大的神经网络放在服务器上面来提供在线服务呢？那么，我们就发现 if you look at the traditional architectures for providing online service with traditional CPU servers. Our architectures was like this. You might have a CPU server with several threads, and then if a user shows up with some data, maybe the user gives a 4x1 vector, right, or some speech data or something, you would give it to one thread, have it compute, and have it output the result. And then if a second user shows up, we have the second thread do the computation for the second user, and so on. Right? So this is a traditional CPU architecture for providing online service. But we found that because we were building supercomputers with many, many GPUs and training very, very large neural networks, we found that we could not take those very large models and put them on a traditional CPU. Right? The CPU wasn't scaling to provide real-time service. So one of the things we did was Baidu was the first large company to announce that we're putting GPUs into production for serving and inference, not just for training. One of the key techniques we developed for that is called batch dispatch. And so what we do is we're putting GPUs into our data centers for serving. And what we do is when a user shows up with some data, we might hold that data for just a few milliseconds, right? Wait a few milliseconds, and wait until a few more users show up with their data. What we do is then batch or put together the data from multiple users. So rather than having 4 vectors, we take these vectors and stack them up into a matrix. So the first user's data, second user's, third, 4 users into, in this illustration, a 4x4 matrix. And then we take all 4 users' data and give it at the same time to a GPU processor, which does processing for all 4 users' data at the same time and outputs all 4 results. And GPU's SIMD, or parallel processing capability, lets it do this very efficiently. And then finally, we take the result and separate it back out into the independent results for 4 users. So we found that this allows us to scale to much larger models and provide service to users online at much lower costs. Just yesterday, I was visiting Baidu's data centers with our director of the data centers, Liu Chao. And one of the trends that we are seeing at Baidu is that with the shift from to using more GPUs and more HPC in data centers, our teams are now putting a lot of work into redesigning data centers to take advantage of this much higher density computation. So today we have teams redesigning power, cooling, in order to enable us to put much higher density racks into our data centers, both for training and for inference. So I expect for those of you that work on data centers, I think there's a lot of exciting work there to be done as well to re-architect our data centers to use more of these high density GPUs. So I said that the first major trend for the rise of deep learning is the scale of computation and scale of data. I think the second major reason, or maybe the second major trend I've seen in deep learning in the last several years, is that deep learning is now able to give much more complex outputs. So here's what I mean. Several years ago, maybe 5 years ago, most of machine learning was outputting real numbers or integers, right? So if you want to classify spam email, you input an email and output 0 or 1. Is this spam or not? Or for object recognition, you input an image and output a number, an integer, telling you what is this object. So one of the exciting trends has been that deep learning is increasingly able to output very complex things, like a sentence or a picture or an audio clip. So for example, the deep speech recognition inputs, inputs an audio clip and outputs an English sentence or a Chinese sentence. Or work we did on image captioning, we can input a picture and output a caption describing the picture, such as inputting a picture and saying, this is a yellow bus driving down the road, right? So neural networks are now able to output sentences or pictures or audio clips or other things, not just integers. Translation, right? Input an English sentence, output a Chinese sentence, or grammar correction. We input a ungrammatical sentence, output a edited, more correct sentence. So I think that clever ways to use this second major trend has been driving a lot of the value and progress in AI and deep learning. Now, of course, one of the major weaknesses, one of the major limitations of AI today is that this type of learning, right, supervised learning, learning rich outputs, still needs huge amounts of labeled data. In the future, I hope we'll have breakthroughs in unsupervised learning, in other forms of learning, but this by itself is enough to transform industry after industry. So, we've talked a lot about how scale, the need to train huge models on a lot of data, how fast computation has been critical for improving AI, for making faster AI progress. We just need to train very large models on a lot of data. There's actually a second reason why AI progress really needs computation, which is that if you look at the examples of neural networks I showed, right, it took us a lot of time, it took us a lot of experimentation to discover most of these neural network structures. I've worked on neural networks for, maybe over 20 years, maybe 20, 25 years. And even today, when I start on a new problem, I don't know what's going to work, right? I don't know what neural network architecture will work. And so our researchers need to try a lot of experiments and try dozens or try hundreds of models before we discover a good model to do things like these. And when you're training on so much data, a speech recognition system trains on 50,000 hours. That's 5 years of data. If it takes you 3 months to run an experiment to train on so much data, then your researchers won't be very productive. And this is the other reason why at Baidu, we've put a lot of effort into optimizing developer efficiency. Because if you are working on a model, you don't know what's going to work. You just have to try a lot of experiments to discover what works. And so we have found that our investments in computer systems to speed up the rate of experimentation, that actually makes our researchers more productive. It makes them able to invent new ideas much faster. And so for us, we've had two emphases for this. One is that we have invested heavily in really our compute platform, hardware, GPU-based, HPC supercomputer, GPU-based compute platform. And the second is we've invested heavily in developing easy-to-use deep learning tools. So we are open sourcing Baidu's deep learning platform called Paddle. Paddle 的重点就是易学易用, right? So our goal is to make it as easy as possible for you to try out deep learning models and experiment and discover what models work for your application. And obviously, Paddle supports using multiple GPUs at the same time. We've reached a stage where we don't train on one GPU. Many of our models train on 16 to 32 to 128 GPUs at a time. So let's see. I have very high hopes for the future of AI. I think that, okay, so 就我个人来讲，我觉得对人工智能的未来充满信心。我就希望几年后， 我们可以使用人工智能来做到这个陪伴机器人啊，也做到个性化私教、硬作曲、机器人医生。我觉得这些产品、这些技术可以为很多行业带来巨大的改变，也对人类带来巨大的价值。这些项目很多都还是正在研究阶段。不过其实我觉得，在这个人工智能的时代，如果你听我们讲“未来”这个字啊，未来有时候很快就会到了。那我想给大家看一个例子，就是我们正在做一个百度医疗大脑的项目，就是这个项目还是在研究阶段。不过请大家看一看这段视频。如果你输入一个问题，比如说你问爸爸发烧了，还出了很多红疹，应该怎么办呢？我们这个百度医疗大脑的软件就可以理解你的问题，也就是问你很多有关你的病情的问题。如果你慢慢回答他的问题，他就可以识别出你的病情有可能是怎么样的，也可以输出一些有关你的病情的信息和建议。对啊，那就是这样的。那么，这个软件当然不可以替代你的医生，而且如果患者想使用这些信息，下一步之前也需要跟医生先讨论。我就希望这类技术，还是在研究阶段。我就希望这种技术未来可以为患者和医生带来很多非常有用的信息。Right. So， 最后呢？我开始讲的这句话就是 AI is the new electricity. I think that we're fortunate to have this amazing GPU platform to build so many AI capabilities on. And at Baidu, one of the things I'm excited about is building AI tools to help not just us. We've already transformed the industry using AI. But one of the things I hope to do at Baidu is building on top of our hardware infrastructure to build the types of AI tools to help all of you, right? To 协助大家进入这个人工智能时代。好，谢谢大家。Thank you.
Thank you. Good job. Thank you. It's great having you on stage with me. You can't possibly overstate the joy and the collaboration that NVIDIA has had with Baidu and Andrew Ng and his team. The work that we're doing together, and as Andrew has already said, is of great importance, and we're super enthusiastic about it. I think that all of the predictions that people have made in the near term, quite frankly, we're going to exceed it. And the reason for that is this. We can't possibly imagine, based on the history that we've had in the limitations and the capabilities of computers, to possibly be able to extrapolate where computing will go in the next several years. And the reason for that is because it's just simply not going to be a straight line. Up until now, we've been talking about training networks, and the networks are going to get larger. We're going to train it with more capability. We're training it so that it can predict more things. It can infer more things. But one of the most important areas of deep learning is ultimately to apply that network on production services, to actually use the network we've trained. This is an area that we've been thinking about for quite some time. Unless you have high-quality networks, the reason to deploy it is obviously not there. But because of all of the work that researchers like Andrew has been doing around the world, we now have so many different types of networks. We have so many companies that have been formed. We have so many industries that have now tried deep learning. It is now time for us to create computers that allows us to take deep learning to billions of people. Ladies and gentlemen, today we're announcing the Tesla P4 and P40. The Tesla P4 and P40 comes in two models. One of them is a GPU that looks like an NVIDIA GPU, very powerful. It goes into a high-performance server. You can put multiple GPUs in a single server. And as Andrew said earlier, data centers are recognizing the importance of using GPUs for inference production. And so as a result, data centers as well as servers are being redesigned to accommodate GPUs like the Tesla P40, the world's first GPU designed for inferencing, based on a brand new architecture called Pascal, has a new instruction set optimized for deep learning, and a new numerical format, integer 8 bits. This is 250 watts and 40 times the performance of a CPU. 40 times the performance of a CPU. And so what this basically says is by putting one Tesla P40, you can replace 40 CPUs. But if you could put 8 Tesla P40s in a single server, you can remove and replace racks and racks of CPU servers. However, there are servers that were designed using the OCP 1U hyperscale standard, and the amount of power delivery capability is limited. And so we designed a second, a cute little, super cute, super energy efficient Pascal inference accelerator. You plug this right into a 1U server, and you accelerate that server with the Pascal GPU. These two represents the new Pascal inference accelerators, designed for hyperscale data centers, designed for production, deployment of neural networks that are trained on NVIDIA GPUs. Okay? The Tesla P4 and P40. The networks that are being created are really, really complex. As we've been saying, the parameters, the model size is increasing incredibly fast. In just 650,000 neurons, or a few 60 million parameters, it has grown by factors of 10. Factors of 10s at a time every year or two. And that trend is going to continue. And so we need faster and faster processors. But we also want to make sure that the networks that we're deploying into the data center is fully optimized. And so we're announcing a brand new technology. It's a software technology. It's an optimizing engine technology. It's called TensorRT. A brand new product. It's a software product that runs on top of our GPUs, TensorRT. It takes basically the network that was trained, runs into optimizing engine. It fuses layers horizontally and vertically. It does auto-tuning. It retargets the network from FP32 to FP16 to N8 wherever it can, reducing the precision that's necessary, and as a result, increasing the throughput, increasing the bandwidth, and reducing the storage necessary. And it does that all automatically. We support all of the major inferencing networks today, BGG and GoogleNet and ResNet and AlexNet, and it also allows you to customize your own layers. TensorRT. It reduces the complexity by sometimes 2x, 3x without affecting the accuracy of the network. It is something you absolutely must do before you deploy this network into your data center. You just get a magic speed up on top of the incredibly fast GPUs you already have. Just that magic speed up. It's really, really fantastic. Ladies and gentlemen, TensorRT. Go to NVIDIA's website to download it right away. So let me demonstrate it to you now. Okay, what you're going to see, the demonstration you're about to see, we have 90 live videos that are going to be streaming through a server. these 90 videos, several things has to happen. You have to ingest 90 videos. 90 videos. You have to decode it, do image processing on the decoded images, and run it through inferencing on the Pascal GPU, as well as the TensorRT optimizing engine. We're going to run all 90 videos at the same time. Now, the application of this is, I guess, relatively obvious. There are so many people who are uploading videos into the cloud. It could be live videos, where we are sharing our live videos with our friends, and yet we would like to be able to find it and notify our friends, or maybe there's some inappropriate material that shouldn't be seen, and so all of that has to be done in real time. What you're about to see is 90 videos running concurrently and being inferenced and classified for what you're seeing in the network. Now remember, you're not just detecting a cat, you're detecting somebody doing something. So this is basically video captioning in real time. Let's go ahead and run it. Okay, so one video at a time. 90 videos, all currently running, streaming through the server. And let's go ahead and classify the videos. Let's do captioning on the videos. Okay, so now the GPU has inferenced, classified all of the videos. So for example, here's one. This is something we all should do more of, push-ups. This is something we should try to avoid, rock climbing. This is a tabla, rope climbing, table tennis, a very good sport. China is very good at it. I used to enjoy this myself. Tai Chi, very good for your health. Looks like a pretty good tennis player here. Notice, so video is being streamed into that server in real time right now, and we're doing inferencing. But suppose I just want to see certain number of these. Like for example, just show me the videos that are playing instruments, musical instruments. We can instantly find them. And so imagine all of this live video is streaming through Baidu's data center. And they want to, for example, only show the Olympics or only show musical instruments and direct those videos to the audience. You can now do it completely in real time. Show me Olympic sports. Speaking of Olympic sports. Pretty amazing. All of it in real time. All of this is completely in real time. And so we have a new SDK. The SDK is called DeepStream SDK. It ingests all of this live video. Ingests the live video into a server. It does the decoding. It does the image processing. All of the necessary inferencing inside an SDK. Manages all of your memory. And does the performance incredibly fast. And I just noticed that I've got to go get one of these things right here. Then you can play ping pong like this at home. This is pretty great. I got to find one of those. Okay, so this is Tesla P40, P4 data center inferencing accelerator running TensorRT, the optimizing inferencing performance engine, as well as the DeepStream SDK. Our first announcement today. You know, Andrew said earlier that deep learning networks are starting to generate and predict and infer all kinds of interesting outputs. Not just image recognition, not just voice recognition, but you're starting to see image and video captioning. But the output could also be a generated output. For example, it could be generating text. It could be generating a story in the future. And one of the things that we would like it to do is to generate art. And so, why don't we go ahead and start running this, and I'll talk while it's running. So this is a video This is a video that's running in real time. Let's go ahead and run it. You can go ahead and start running it. Okay, so this is a video that's running in real time. It's running through our GPUs in a data center. And the GPU, the network, has already been trained to generate a new form of art based on the video that it sees. And so there's all kinds of, isn't this beautiful? This is currently being generated in real time. Every single pixel that goes into the network comes out as a different pixel, and the pixel has been infused with art that it has learned from all of the other art forms that the network has been exposed to. In this particular case, this is Picasso. So it turns your video into Picasso. Isn't this beautiful? All completely in real time. It's just incredibly beautiful. And with a high-performance GPU, the ability to inference in real time, we can now generate art in real time, doing it for, in this case, HD video. And there's all kinds of different styles you could apply. So this style is beautiful. We saw Picasso earlier. And there's one particular style that I would love for you to see. And this, hopefully it comes up next. Oh. That's incredible. That's what pandas look like to Picasso. This is incredible. There's one particular style I think I'm going to make all of us wait for. It's hopefully coming up. That style is just beautiful. Each one of these styles were learned by the GPU. Isn't this amazing? Chinese pencil art. This is just utterly stunning. And so the network were trained by all of these different art forms. And then we simply give it a new video, new source, and we say, apply that art form, apply that style to this new video. And so as you could see, deep learning is not just limited to object recognition. It's not just limited to voice recognition. The whole concept of deep learning could be applied in a surprising number of ways. And we're starting to see researchers and developers apply deep learning in so many different imaginative ways, and that's spreading all over different industries. Thank you. Deep learning started in researchers, laboratories all over the world. Andrew Ng, Jeff Hinton's laboratory, Yann LeCun's laboratory, all over the world, researchers, and here in China, in the United States, in Europe, researchers all over the world apply GPU deep learning to do their AI research. It then quickly became commercialized by the companies that have a large amount of data. And those companies are hyperscale companies. And these hyperscale companies are using the vast quantity of data that they have to train their networks, their GPU networks, to develop interesting networks. Now they're in the process of deploying it into production. You heard earlier, Baidu is now redesigning their data center, redesigning servers, and it's starting to accommodate GPUs, not for training, but for inferencing. And we're going to see GPU used for inferencing because of its incredible throughput advantage and its energy efficiency in data centers all over the world. But we're also starting to get ready for all of these startups that have developed great ideas as they go to production. Deep Instinct is using deep neural nets for understanding cybersecurity, to recognize the very subtle patterns of a hacker. Deep Genomics is using deep learning to sequence the human genome. We know that if we could figure out a way to sequence human genomes fast enough, we now have editing tools like CRISPR. The combination of these two breakthrough technologies could help us relieve all kinds of human disease and human suffering. Drive AI is using deep learning for self-driving cars. And you saw the example of live video from a company called Artisto, and Prisma applies a very similar technology for still images using deep learning for art. Each one of these applications, deep learning is being applied in a different way. However, the fundamental technology is the same. And as all of these companies now start to go to production, Tesla P40 and Tesla P4 are perfect for their deployment. We're seeing all kinds of great startups here in China. Colorful Cloud, amazing achievement what they're able to do. They could predict the weather 8 minutes from now, according to what I've learned. What is Beijing's weather going to be like in this area in a few minutes? By using deep learning, they can predict, they can infer from all of the inputs that they get from around the city what the weather will likely be like. We have a company called 7invention using eye tracking for human-machine interaction. This is going to be a really important technology in the future of VR and AR. Medical imaging from Infervision, early detection of disease, face recognition from Authenmetrics, product recognition detection search from Malong, and Laya for personal concierge application. This particular application in this field, AI agents, is going to make our lives a lot more convenient in the years to come. And so this is all about inferencing and the production use of the networks that we have created in training using Pascal, Tesla P100, and DGX1 for training, IBM servers for training, then using Tesla P40 and P4 for inferencing, so that all of these applications could go into production with affordable data centers, with response times that are incredibly fast and delightful. Now let's change gears and talk about devices. We're going to have embedded devices with intelligence infused with deep neural nets all over the world. This, in my opinion, deep learning and deep neural nets is what's going to make IoT really amazing. It's not just the fact that a device is connected to the internet. It has to be an intelligent device connected to the internet. And this is an area where we can also add a great deal of value. We're going to see all kinds of interesting devices. Anything with a sensor is going to be an intelligent device. With a camera sensor, it could be a smart camera. Not only does it detect and record intrusion, it might actually recognize who it is at the door and just simply tell you that your son's friends at the door would like to come in and play. That the person delivering the mail, the post office person, is going to deliver a package to you. Open the door, open the gate. And so having the ability to have intelligent cameras all over your house is really a fantastic way. And then, of course, there are all kinds of interesting devices. The Jibo, it's a personal assistant that recognizes who you are, understands what you say, tells you a story, tells you what the weather is, turns on the music, so on and so forth, just like the Amazon Echo. You're going to see intelligent devices like drones with deep neural nets integrated into them so that they could fly autonomously and navigate around environments in search of something or deliver a product. There's a company in Europe called Starship. They have a little tiny robot, and when you have a delivery, they simply put it in the robot, and it finds its way through a neighborhood and delivers it to your house, completely autonomously. So these intelligent devices are going to need artificial intelligence to make them possible. And the technology is finally here. It's called deep learning. One of the most exciting areas, one of the most important areas of deep learning and IoT, that intersection, is potentially AI cities. By 2020, we're going to have 1 billion cameras all over the world. Intersections, public areas, airports, train stations. We're going to have cameras all over the world. And it's simply impossible to have real people sit in front of those cameras, sit in front of those monitors, and monitor what's happening all over the world. 1 billion cameras. 1 billion cameras. 30 billion images per second will have to be inferenced. Just now we saw 90 videos. We're going to have 1 billion videos all over the world, and we would like to apply intelligence to that. To recognize when somebody had an accident, to recognize when a pet or a child has been lost, to recognize when somebody is about to experience harm, to keep people safe. These intelligent cameras are going to be all over the world, and by applying deep learning and applying intelligence to them, they could basically operate autonomously. And whenever there's an accident, a camera would know instantaneously and alert people to come and help you. 30 billion inferences per second. The total amount of GPUs necessary to inference that much video in real time is about 10 million P40s. 10 million P40s. 10 million servers will have to be sprinkled throughout the world in order for us to apply intelligence to all of those videos. Well, there's some really innovative companies in China working on this very problem. Today, I'm super delighted to announce one of our first partners in this area. Hikvision is a world leader in AI, and applying their leadership of deep learning and AI to the application of IVA, intelligent video analysis, so that we could have these network of cameras all over the world and apply artificial intelligence to keep people safe. The AI city, not just a smart city, but an artificial intelligence city, a city that's essentially a thinking, breathing robot that keeps people safe. Hikvision applies deep learning in their servers. And the server design they applied, they trained the network on DGX-1s with the enormous volume of data that they've collected to recognize objects and situations. That network is then put into a server called their blade. That blade has 16 little embedded CUDA processors inside. Thank you, Paul. Each one of the blades has 16 of these little Tegra processors. Okay? 16 of these little tiny Tegra processors. 16 of them. And video comes in, it's decoded by the Tegra processor, Tegra TX1. The image processing is done on the Tegra TX1, and the inferencing is done on a Tegra TX1. These 16 little processors has better performance than 21 CPU servers. As a result, it takes 1/20th the space. 1/20th the space. This little tiny 1U server replaces 20 other servers. 1/20th the space and 1/10 the power. These servers can be deployed all over the world. Hikvision is the world leader in intelligent video analysis, and this is just an incredible, great product that they have created, and they're in the process of taking it to market today. I'm super proud of our relationship with them. This is really going to be a breakthrough product. I think this is going to bring in, very much so, the foundation of the future AI city. Let's give them a round of applause. This is such a large problem, it's going to take a whole lot of companies to solve it. And here in China, we have some of the world leaders in intelligent video analysis, Hikvision, Dahua, and Univision. All three of them are NVIDIA partners for training, and NVIDIA partners for the actual inferencing of the smart cameras. Transportation. Transportation is a $10 trillion industry. This is one of the largest industries in the world. a $2 trillion automotive car industry, $5 trillion taxi, shuttle, services, transportation as a service industry, trucking industry on top of that, altogether $10 trillion, a massive industry. There's so much we could do to improve this particular industry with AI. And one of the most exciting areas of development, of course, is the self-driving car, autonomous cars. Now, autonomous driving promises to bring in a world where it is simply safer, where because cars with AI could be thinking all the time, watching all around, always in attention, never gets tired, sensors everywhere, and so it has just superhuman capabilities to keep you out of harm's way. It can increase the productivity of your fleet of cars and fleet of taxis. And of course, with fewer accidents, insurances will go down. Just the amount of capabilities necessary to make this dream possible has never been possible until today. We've not been able to understand what it would take to create a world of autonomous vehicles until deep learning with GPUs made it possible for us to finally believe that an AI car is possible, that an artificial intelligent car is possible. Now, first of all, let me tell you why I call it an AI car. An AI car is not a car with a smart detection camera. It's not a car with just radar. Radar and cameras are detectors. However, in order to have autonomous driving, you need a lot more capability than detecting an object in front of you and stopping. Artificial intelligence includes perception, seeing, hearing, and understanding what is around your environment. Number 2, reasoning. Based on what you see, what is the best course of action? Should you continue to drive? Should you change lanes? Should you stop? Or should you come to a more cautious, slower speed? Or pull to the side? The car reasoning in all of this infinite amount of conditions in the world is a very complicated problem. And then lastly, once it reasons about the environment, it has to create an action plan. What is the course of action? What is the course of action? This is end-to-end an AI problem. It's an AI computing problem, not just an object detection problem. AI computing, as you've been hearing, is finally here. We can now finally, for the first time, imagine the end-to-end solution to realize this vision of an autonomous vehicle future and a hope of transforming and revolutionizing this incredible industry, $10 trillion industry. I'm going to show you a couple of videos just to give you a sense. The first video, this is running on a little tiny computer like the one I just showed you. And what we're doing here is we're detecting the areas in front of you that are safe to drive. Not just detecting the object to stop. Detecting the object to stop, object detection. This is recognizing in front of you what is a place that's safe to drive. Okay? So it's reasoning about, it's looking in front of you and it's thinking, where can I drive? If there's a person in front of you, of course, you should stop. It's not safe. You should see that it's safe to drive all the way up to the bottom of that car. You could see that it's safe to drive except for the curb and the cars parked around you. That's safe space. The opposite of recognizing objects. Because how many objects would we have to recognize in order to conclude that we are safe? There are cars, there are cows, there are trees, there are houses, there are bicycles, there are pedestrians. There are so many things to detect. And there are so many things that would be unexpected for us to detect. But if we detected what was safe, we could understand where to drive. We also want to reason based on the things that we see what is the volume of that object? And so this is 3D car detection. Not just the poster of the car or the image of the car, but what is the 3D volume of that car? Because we might decide to turn in front of it. We might decide to pull in front of it in a lane change. Okay, so these are some of the examples of capabilities. There's so much more software that goes into AI computing, and what I wanted to do is I've integrated everything and we put it into one car, the NVIDIA self-driving car. We called this car, this little robot, the BB-8. Now what you're about to see, this video, what you're about to see is BB-8 driving in a variety of road conditions, as well as a variety of environmental conditions. The important thing to realize is this. BB-8 was not programmed to perform any of the actions that you see. BB-8 was not programmed to perform these driving skills. BB-8 learned it by watching us. Okay, so BB-8 learned how to drive by watching us. Let's take a look at it now.
Oh yeah, good. The universal sign for auto.
Everybody has to learn how to drive somewhere. And most people learn how to drive in a parking lot, so did BB-8. But very shortly after, we took BB-8 out into the road. There are no lanes to detect here. And yet we, as humans, know how to drive around it.
I'm not touching anything.
There's so many things that could be in front of you. And yet we, as humans, somehow learn to drive around it. Just because a place is of construction doesn't mean it's not safe to drive through. BB-8 is currently, look at that. Is that amazing? And just like us, we could learn to drive in one country or one state, but we can drive everywhere once we learn how to drive. This is BB-8. Learned how to drive in California, and it's driving in New Jersey. And it learned how to drive at night. And it's not scared. And there are no lanes, nothing to follow.
Got it.
This is just the beginning of our work, but I wanted to show you that with artificial intelligence technology and with an artificial intelligence AI computing supercomputer in the car, and with enough richness in algorithms and with enough training that we can teach these intelligent devices how to perform tasks that are impossible for us to write software to do. And this is the reason why we believe that because of AI, we are going to see an intelligent device revolution. This is an area that is going to see enormous amounts of innovation. However, autonomous driving is not just a simple thing. We are still far from having fully autonomous vehicles on the road all over the world. However, we're making incredibly fast progress. Autonomous vehicles and autonomous driving is also not a point product. It is not ADAS. It is not detect a car in front of you and stop the car. It's not about stopping the car, it's about driving the car. It's about driving the car and keeping everybody out of harm's way while you're driving the car. And there's a lot of different varieties of autonomy. Autonomous vehicles is not just one destination, it's not just one style, it's not just one product. Autonomous vehicles are going to find its way into society, and autonomous vehicles are going to add value to society in a variety of ranges. starting from just making highway driving much, much more safe. Highway driving much, much more safe. We call that auto cruise. And on the other extreme is full autonomy. There's no driver in the car. If there's no driver in the car, that car's ability to perform would be largely impossible unless the percentage of failure is so low, it is basically perfect. We're shooting for 99.999999% accuracy. And notice, as you saw earlier, accuracy of a network and the total amount of computation of the network is related. If you want accuracy, you need to have more flops. If you want accuracy, you need to have larger models. And if you have larger models and you still want to operate it in real time, you need to have more flops. If you want to have more cameras around the car, you need to have more flops. And so in the other extreme, autonomous vehicles requires many supercomputers in order for the vision to be realized. We created an architecture called Drive PX2. And people really asked us, why do you need so much computation? Well, you've finally seen it. Because autonomous driving is not ADAS. Autonomous driving is an AI problem. It's an AI computing problem. And depending on the range of capability you would like to offer, you need a different amount of computation. We created Drive PX2, the world's first automotive AI computing platform. It is scalable. It has enough performance and capability to do perception AI, reasoning AI, and driving AI. And I showed you examples of each one of the three just now. It is an AI supercomputer. It's an AI supercomputer. It is rich with AI algorithms. And one of the greatest things that every car in the future will have to do is contain a lot of software. It is going to be one of the most complex computers that we know. A sensor fusion, high-performance computer. And then lastly, any autonomous computing platform that is going to be of value to the world has to be scalable. Because we simply don't know exactly what people want to do. Every car company wants to build something a little bit different, and there are many car companies that are building all three of them. From auto cruise to auto chauffeur. Auto chauffeur means this. You can go from location to destination by simply telling the car where you want to go. You could say, take me home. And the car pulls onto the road, pulls onto the highway, takes you all the way back home. There's still going to be places where the car simply can't perform because the environment is too complicated. And that's where you take over. But you're still in the car. You now have an auto chauffeur that allows you to go from point to destination, from location to destination, by just simply telling it where you want to go. And then, of course, lastly, full autonomy. Cars that are coming around like a taxi, you simply hail it on your phone, and in the future, it will be a fully autonomous taxi coming to pick you up. Now, today, we showed this year at CES a full autonomy-capable platform. And our customers are putting multiple of these systems inside a taxi. However, we have now shrunken the smallest version of it, called Auto Chauffeur. This version, called Auto Chauffeur, is now in production. The NVIDIA Drive PX2 Auto Cruise, one little tiny computer, 10 watts, allows you to do perception, reasoning, and driving on the highway, support multiple cameras, sensor fusion with radar if you like, and while it's doing driving, it is also continuously doing localization and mapping. That is incredibly important to the future of autonomous driving. And the reason for that is because the millions of cars that are on the road needs to update a high-definition map that's in the cloud all the time. And so this particular processor will also do simultaneous mapping. The Drive PX Auto Cruise is the foundation of our partnership with Baidu. Our partnership with Baidu that Robin and I announced, thank you, this is the Drive PX2 Auto Cruise. Robin and I announced at the Baidu World a partnership between Baidu and ourselves. The question is why? Well, the reason for that is because in order to have high quality autonomous driving, you need to have an AI supercomputer in the car, AI algorithms that are doing perception, reasoning, and driving, rich amount of software, and it has to be connected to an HD cloud that gives you information around your surroundings. No company has been able to provide this level of capability on an open platform so that all car companies can benefit from the service until now. Between Baidu and NVIDIA, we have two companies with enormous scale that allows us to solve the problem of autonomous driving from in-car computer all the way to the cloud computer, from the algorithms in the car all the way to the algorithms in the cloud, and for it to be connected all over China. This partnership is incredibly exciting, and what's unique about this partnership is that whatever is developed in this platform will be made available to car OEMs who would like to participate. It's an open platform. So not only will Baidu use it for their own self-driving taxis and their self-driving cars, it would also be a platform by which we can offer to other OEMs. Our partnership with Baidu is incredibly exciting, and it adds to our fleet of partnerships around the world. We now have partners in Singapore, Nutonomy. The taxi is already driving around in Singapore. Volvo in Europe has the Drive Me cars with NVIDIA's Drive PX2s, and they're also on the road. WePod is a shuttle that you can simply hail with your smartphone, and it comes and picks you up. And then, of course, you saw the NVIDIA BB8. There'll be so many other partners that you will hear about. What's really, really important is simply this. The AI computing model, AI computing, has finally made it possible for us to realize the dream of autonomous vehicles. And together we could revolutionize a $10 trillion industry. So let me summarize what we heard today. Deep learning is a problem, is a new computing software challenge. It's a new computing model that starts from training to data center inferencing to make that service available to everybody, to in-device intelligent devices. It's an end-to-end problem. It's an end-to-end computing model, and will touch every computer that we know of. NVIDIA's strategy is to create an end-to-end learning, deep learning platform. We started with Pascal and DGX-1, the world's first GPU that has been designed and optimized for deep learning. And DGX-1, the world's first computer that was designed from the ground up for AI supercomputing. You heard about our announcement of the Tesla P40 and P4, the first inferencing accelerators for data center, as well as the TensorRT optimizing engine for inferencing. And we announced the Drive PX2 Auto Cruise and the availability of Jetson TX1s for applications like AI cities and AI cars. Both of those platforms comes rich with software. Rich with software. In the case of Jetson, it comes with CUDA, it comes with TensorRT, it comes with computer vision algorithms. In the case of Drive PX2, it comes with a high-performance sensor fusion operating system, the AI algorithms that go along with self-driving, and of course, our partnership with Baidu connects it all the way to the cloud. We also announced today some really fantastic new partners. IBM will take NVIDIA's platform along with the Power 8, and with their might and their reach of enterprise IT bring AI to the enterprise. We announced 3 partnerships today for AI City, one of the most exciting areas in IoT and artificial intelligence, to keep our cities safe for all of our citizens. And of course, a revolutionary opportunity that we're pursuing with our partnership with Baidu. I think that it's hard to overstate this discovery. It started in 2012. Arguably, research in deep learning had gone on 20 years before that. But it wasn't until the great discovery of young researchers in using deep learning on GPUs that started the GPU deep learning revolution. Now we have the breakthrough technology that will accelerate one of the most exciting fields in computers and a dream we've all had for many decades, artificial intelligence. Artificial intelligence has the promise of solving problems that no software written by engineers has been able to solve until now. We talked about AI for transportation. You can imagine AI for detecting diseases earlier, for recommending a diagnosis because of your family heritage, because of the symptoms of your disease, and because the vast amount of data that's available in publications and research all over the world, that when you put that artificial intelligence in the hands of doctors, they could make better diagnosis to cure your disease. And of course, we now have this amazing technology for editing genes. It's called CRISPR. You may have heard about it. It's one of the most important technologies in genomic life sciences ever. And now combine that with the ability to use deep learning to map the human genome. The combination of those two capabilities could very well discover new medicines and put to end disease that we've been fighting for so long. AI will revolutionize healthcare. And then, of course, you've seen examples of the first robot for AI. It's called the car. But in the future, you're going to see robots that can learn motor skills all by itself. Just by understanding what the goals are, which is opening a bottle, could be putting a hammer on a nail, it could be picking up a ball, it could be kicking a soccer ball. By learning, understanding what the goals are, the robots could learn the motor skills by itself. If we just had artificial intelligent robots, they can do tasks that we can't do. They could perform tasks that are harmful for us to do. They could keep our elders' lives productive by assisting them around the house and around their lives. The ideas for AI can go on and on and on. But one of the things that I'm super excited about, and I'm really pleased that you came here to learn about the potential of GPU deep learning. This is simply too important of a new computing approach not to learn. It is simply too important. GPU deep learning is the most important advance in computing in recent history. And we believe that this is going to be the next era of computing. This is going to be the era of AI. And some people call it, in fact, the beginning of the next industrial revolution. These are really exciting times. We are dedicated to continue to advance AI computing as the world's AI computing company, to partner with all of you to advance this incredible new opportunity. Thanks for coming to GTC. Have a great GTC.